Hello, physics students, and welcome to our unit about rotational motion. We're going to start this unit by looking at how we measure rotational motion. We're going to start by looking at the difference between radians and degrees. We'll take a look at what angular displacement is and how to calculate it. We'll look at angular speed and angular acceleration. And finally, we'll compare linear and angular rotational kinematic equations. So let's start by describing what rotational motion is. It simply is the motion of a body that spins about an axis. If we think about the picture in the previous frame of the Ferris wheel, every point on the wheel undergoes circular motion around the center. We're going to analyze the motion about the center by just choosing one point on the Ferris wheel. Let's choose one little light bulb on that Ferris wheel and analyze its motion. So to analyze our motion, it's convenient to set up a fixed reference line. So that is represented right here. Here's our bulb and here's the reference line. And we can draw a line from the center of the wheel to the bulb. I just drew that in orange. That represents r, or the radius. So here we are at time t equals 0. After some time interval, delta t, we arrive at this diagram where the bulb has moved from its original position to this position. Notice that the radius, the line for the radius, has also moved through this angle theta. The bulb itself has moved along this path, and that is its distance, s. That s represents what is called the arc length. In science, angles are measured in what are called radians, abbreviated RAD. And when our angle is equal to s divided by r, when s and r are equal to each other, we say that theta equals 1 radian. That would be the definition of a radian, when the arc length and the radius are equal. So the radian is a pure number with no dimensions. That is because the arc length is a distance and the radius is a distance, and those units cancel out. And so radian is what we use as a unit. However, it really is a unitless pure number. If we think about our example of the light bulb once again on our Ferris wheel, and we move that Ferris wheel through a complete rotation, 360 degrees. Move that light bulb through 360 degrees. The arc length, s, at that point, is equal to the entire circumference of the circle, which is 2 pi r. We can substitute that 2 pi r into our arc length, and we can then cancel out the two variables of r. So we can see that 360 degrees is equal to 2 pi radians. And I added, remember, radians, even though this is a pure unitless number, that's what radians are. So here we have a circle depicted with both degrees and radians, and this is not the only numbers of degrees that we can convert into radians. We can convert any number of degrees into radians. We simply multiply the angle measured in degrees by 2 pi divided by 360 degrees, and in this way we can do that conversion. We can simplify that by this equation right here. Theta in radians is equal to pi divided by 180 degrees times theta in degrees. So by plugging radians in here, we could convert radians into degrees, or we could plug in our angle in degrees here and convert into radians. Now that you know how to convert degrees to radians, we can talk about angular displacement. Angular displacement is simply the angle through which a point, line, or body is rotated in a particular direction and around a particular axis. So angular displacement is represented by this delta theta. Delta theta in our diagram here is simply theta 2 minus theta 1. Here is theta 2, and here is theta 1. Those are the two angles, and those are measured in radians. angular displacement is equal to the change in the arc length, delta S, divided by the distance of the bulb from the axis of rotation, that would be R, the distance of the bulb from the axis of rotation. This is the axis of rotation. For this class, we are going to consider that S is positive when our point rotates counterclockwise, and it will be considered negative when our point rotates clockwise. In other words, angular displacement will be positive when the object rotates counterclockwise, and it will be negative when the object rotates clockwise. And again, this is simply restating what we said about angular displacement being the change in theta in degrees, and counterclockwise we will see positive angular displacement. Clockwise we will see a negative angular displacement. Let's try an example and see if we can use our formulas that we've been given. Let's say that a girl is riding on a carousel that is rotating clockwise. And you know, this picture, it's showing that it's rotating counterclockwise. I realize that. So flip that around in your mind. It will be rotating clockwise, and she travels through an arc length of 10.0 meters. If the girl's angular displacement is 155 degrees, what is the radius of the carousel? I'm going to start by writing down what I know. I know the angular displacement is negative 155 degrees, again, because we're going clockwise, and we're told the angular displacement is 155 degrees. I'm going to assign a negative value since it's clockwise. I will assign a negative value to my delta S also because of the clockwise direction. Delta S is 10.0 meters negative. And I want to find the radius of the carousel, so R equals question mark. It's my unknown. First, I need to convert my degrees for delta theta into radians, and I can do that using our formula that we just learned. So I simply plug my value in for delta theta in degrees, which is 155 degrees. And when I plug those numbers into my calculator, I get my angular displacement in radians as equaling 2.71 radians. Oop, I forgot it's a negative 2.71 radians, so I put that negative value in there. Next, we will use our angular displacement equation and plug values into that and solve for R. Here are this is my angular displacement in radians, and this is the delta S, the change in arc length that we have been given there. And I get, when I solve that algebraically, R equals 3.69 meters. Now let's take a look at angular speed. We needed to learn about angular displacement first because to talk about speed, we're going to look at the displacement per time. And that should ring a bell with you from our linear definitions. Remember, when we talk about linear motion, delta D represents our change in displacement. And our average velocity could be found by taking the change in displacement divided by the change in time. We're doing the same thing with angular speed. We're looking at the average angular speed as equal to the change in displacement, angular displacement, divided by the change in time. So there's a definite correlation here. Don't get scared off by the Greek letters. Units, when we talk about angular speed, are in radians per second. Occasionally you might see units in revolutions per unit time if you come across that. This is just the way you can convert that. We will use units in radians per second. Let's try an example. Let's say your classmate, holding their feet off the floor, spins counterclockwise in our rolly chair in the classroom with an average angular speed of 3.5 radians per second. In what time interval will your classmate's feet, holding them still of course, have an angular displacement of 8.0 pi radians? So let's write down what we know. We know that we have an angular displacement of 8.0 pi radians. We also know the average angular speed because that's been given to us. And something to note that I forgot to mention, this letter is a Greek letter called omega. And just so you don't confuse it, this is the lowercase omega. This is the Greek capital omega. So you've seen that perhaps already when we're talking about resistance. It's the unit. It represents the units for resistance, which we'll talk about later on. But this is the omega that we use, the lowercase omega, and that represents the average angular speed. Delta t will be our unknown that we're being asked. In what time interval will your classmate's feet have that displacement? We can use our equation for average angular speed because we already have our angular displacement in radians, and so we can plug our values into our formula. And when we go ahead and do the algebra here, we get delta t equal to 7.2 seconds. You can, of course, rearrange the equation before plugging values in so that delta t would be equal to the average angular speed divided by the angular displacement, or you could plug the values in and then do the algebra after. Either way is fine. Now we're going to talk about angular acceleration, and it's very similar to linear acceleration. Remember, when we talk about linear motion, our average acceleration is equal to the change in velocity per the change in time. And it's the same idea when we talk about rotational motion. In rotational motion, we're going to designate acceleration with an alpha character. There's our alpha. The average angular acceleration in this case is going to be equal to the change in angular speed divided by the change in time. So really the only difference between these are in the Greek letters that we're representing. This is for the angular motion, whereas this is for the linear motion. Again, we can look at the change in angular speed as the speed for 2 minus the speed for 1, and change in time is time 2 minus time 1. The units for angular acceleration should be pretty obvious. If the units for angular speed were radian per second, the units for angular acceleration are going to be radians per second squared. Now let's do an example. Your car's tire rotates at an initial angular speed of 23.0 radians per second. I'm going to go ahead and write that down. That's going to be my initial angular speed. Now, you accelerate, and after 3.0 seconds, the tire's angular speed is 28.0 radians per second. I'm going to go ahead and write those values down. I know my angular speed, number 2, is going to be 28.0 radians per second, my final angular speed. And I know my time interval is 3.0 seconds. So now we're being asked, what is the tire's average angular acceleration during the, 3.0 second time interval? So my average angular acceleration is my unknown. I can use my equation for average angular acceleration, and I can use this change in angular speed divided by my change in time. I can plug the appropriate values in. I already have my average angular speed is in the correct units, radians per second. My time is in the correct units. It's in seconds. That gives me an average angular acceleration of 1.7 radians per second squared. So far we have been talking about rigid objects, such as a car tire, or a bike tire, or a carousel, or a Ferris wheel. For rigid objects, all the points on that rotating object have the same angular acceleration and angular speed. If they did not, let's take this carousel. If a point out here on the carousel had a different angular speed than a point in nearer to the axis of rotation, this would be changing shape. It would not be a rigid object. So for rigid objects, all points rotating that are rotating on that rigid object have the same angular acceleration and angular speed. So we have been comparing angular and linear quantities all along. Here is just a nice little table looking at the angular substitutes for those linear quantities. Here are the angular substitutes for these different linear quantities. And here is just a comparison of our kinematic equations for angular rotational motion and linear motion. And you can just directly compare these to each other and see how those variables are changed for the different types of motion. Just a little note is that omega represents instantaneous angular speed of the rotating object, not the average angular speed. So let's look at one last example using angular kinematics. The wheel on an upside down bicycle moves through 11.0 radians in 2.0 seconds. I went ahead and wrote these values down. What is the wheel's angular acceleration if its initial angular speed is 2.0 radians per second? So I'll write this down as well. And I'm going to look for how I can find my wheel's angular acceleration. So I will use my second angular kinematic equation from the previous page. Here I can substitute all the values in that I need to, and I can solve for alpha. And alpha is 3.5 radians per second squared. Again, you will not need to memorize these. You will always be able to look at them. So don't get scared about the fact that there are some of these equations. You'll always be able to look and see which one will be best suited to your situation. Advanced ideas, make up your own problems. Try to solve an angular displacement problem by using the formula for the circumference of a circle and the percent of the circle traveled. See if you could try one of those. And if you have other questions, other ideas, please come up with those. And I look forward to seeing what you come up with, and we'll see you in class.